Earth's most dramatic landscapes were carved not over millions of years, but in a matter of days. This is the story of ancient megafloods, geological events of almost unimaginable power that could rewrite entire continents in a single, catastrophic season. By the end of this exploration, you will understand how to read the planet's most violent chapters written in stone. Our entire understanding of geology was once built on the idea of slow, steady change. But what if the most important changes happened in a flash? How can we recognize the evidence of a cataclysm that lasted only weeks within a rock record that spans eons? The answers lie in some of the most bizarre and beautiful terrains on Earth, holding clues to a past far more volatile than we ever imagined. What does it feel like to stand in a landscape shaped by a single, terrible day? That single, terrible day was a geological instant. In the language of our planet, an instant can be a violent season, a catastrophic year, or a relentless century. It is a span of time so brief it barely registers on the grand timeline of Earth's history, yet its consequences are etched permanently into the bedrock. This idea challenges a very old and comfortable story we told ourselves about how the world works. For generations, the guiding principle of geology was uniformitarianism, often summarized by the phrase, "The present is the key to the past." This view held that the slow, gentle processes we see today, like a river carving its bank grain by grain over millennia, were entirely responsible for shaping all the landscapes we see. It was a vision of an Earth that changed with infinite patience, but the evidence of these megafloods tells a different, more dramatic tale. It whispers of catastrophism, the idea that our planet's history is punctuated by sudden, violent events of extraordinary power. These are not mutually exclusive concepts. Think of Earth's story not as a slow, steady novel, but as a long, quiet biography interrupted by a few explosive, plot-twisting chapters. Most of the work is done by the patient drip of water and the steady push of wind, but the most dramatic turning points, the events that set the entire course for what comes after, happen in a furious rush. So when we speak of a geological instant, we are speaking of that furious rush. It is the difference between a sculptor patiently chiseling a statue over a lifetime and a titan swinging a hammer once to cleave a mountain in two. Both shape the stone, but only one does it in the time it takes to draw a single breath. This new story of a volatile Earth needed a place to begin, and it found one in a landscape so strange it looked like it belonged on another world. Eastern Washington state holds a secret written across thousands of square miles, a region known as the Channeled Scablands. To stand there today is to walk through a geological ghost story. You see not the rolling hills or gentle valleys of typical erosion, but a torn and scarred plain, deep, sheer-walled canyons called coulees, cut through the bedrock without any river in them. The ground is littered with enormous potholes, some as big as houses, and scattered islands of rock that stand alone like ships run aground on a dry sea. Most telling of all, stretching across the desert floor are giant ripple marks. These are not the small ripples you see in a creek bed, but waves of gravel and rock 30 feet high and hundreds of feet apart, frozen in stone. It is a landscape that makes no sense if you believe only in the slow drip of water. In the 1920s, a geologist named Harlen Bretz spent years mapping this bizarre terrain. He was a meticulous observer, a man of careful science, and the evidence he gathered led him to a single, inescapable, and utterly heretical conclusion. This was not the work of millennia. It was the work of a flood, a catastrophic deluge of almost biblical scale that had ripped across the land in a matter of days. He called it the Spokane Flood. To the scientific establishment of his day, steeped in the doctrine of gradual change, this idea was not just wrong, it was offensive. It was a throwback to unscientific myths. Bretz was ridiculed. His peers could not accept that a single event, a geological tantrum, could accomplish what they believed required eons of quiet work. They demanded another explanation, any explanation that fit their slow and steady worldview. But Bretz had the evidence written plainly in the rock. He simply asked his colleagues to look at what was actually there, to read the story the land was screaming at them. The conflict that followed would become one of the great turning points in how we understand our planet's past. The evidence Bretz compiled was a catalogue of the impossible. He measured those giant ripples, understanding their physics. Water can only create ripples that large if it is moving at tremendous speed and depth, a torrent hundreds of feet deep roaring across the landscape. He traced the paths of house-sized boulders, erratic stones of a distinct granite, and found they could only have come from mountains hundreds of miles away. They had been plucked from their bedrock and carried like pebbles in a current of unimaginable force. Most damning to the old view were the channels themselves. These were not river valleys carved slowly by a meandering stream. They were immense, steep-walled trenches, sometimes miles wide, that cut directly through solid basalt bedrock. They formed a sprawling, interconnected network that looked like a colossal, dried-up river system, but one that had operated with a ferocity that defied all conventional models. Bretz argued this was not the work of any normal river, but of a singular, catastrophic outburst, a deluge that had scoured the land down to its bones in a geological heartbeat. His hypothesis was a direct challenge to the entire foundation of his field. To the geological establishment, it sounded like a retreat into pre-scientific myth, a violation of the core principle that the present gently explains the past. The most powerful rebuttal came not from evidence in the field, but from a simple, glaring question posed by his critics, where, they demanded, could such an impossible volume of water possibly come from? Without a source, Bretz's magnificent flood was just a story. He was mocked in professional circles, his life's work dismissed as the wild fantasy of a catastrophic. For decades he stood virtually alone, a heretic with a map, armed only with the stubborn facts written across 1,000 square miles of scarred earth. The scientific revolution he sparked would not be completed by him, but by someone who would find the missing piece, the source of all that water, hidden in plain sight. The answer to that question lay dormant in the mountains, waiting for a geologist who could read a different kind of map. While Bretz faced skepticism in the east, a United States Geological Survey scientist named Joseph Pardee was studying the mountains of western Montana. There he found a story written not in torn canyons but in silent shorelines, etched along the steep slopes of mountain valleys, high above any modern river, were a series of crisp horizontal lines. These were ancient beaches, the bathtub rings of a vanished lake. Pardee pieced together a staggering picture. During the last ice age, a lobe of the immense Cordilleran ice sheet had acted like a giant natural dam, blocking the Clark Fork River. Behind this wall of ice, water had pooled for centuries, creating a vast inland sea he named Glacial Lake Missoula. This was no ordinary lake. At its fullest, it contained more water than Lake Ontario and Lake Erie combined. Its surface lapped at those high shorelines, over 2,000 feet above the valley floor, holding back a volume of water almost impossible to visualize. Think of all the water in one of the American Great Lakes, then double it, and then picture it all stacked up behind a single, fragile dam of ice. The potential energy stored in that elevated sea was monumental. It was a geological powder keg. Pardee realized that if that ice dam were to fail, even partially, the entire contents of Lake Missoula would be released in a catastrophic torrent. The water would have nowhere to go but west with unimaginable force, rampaging across the Columbia Plateau directly toward the strange landscape Bretz had mapped hundreds of miles away. Pardee had found the source. He had identified the reservoir, the dam, and the terrifying mechanism. but for his hypothesis to move from a compelling idea to accepted fact, he needed to find the dam's broken remnants and the specific, violent signature of its failure. Pardee found that signature not in a single broken wall, but in the rhythm of the land itself. The true scale of the catastrophe was even grander and more terrifying than a single flood. The Channeled Scablands were not carved by one event, but by many. Modern research reveals that Glacial Lake Missoula did not just fill and empty once, it did so repeatedly, perhaps dozens of times over 2,000 years. The Ice Age was a pulsating beast, its icy lobes advancing and retreating with the climate. Each time the ice dam reformed, the vast lake would begin to fill again, a process taking decades. And each time the dam reached a critical point of pressure or was weakened by a slight warming, it would fail catastrophically. The result was a series of geological heartbeats, each one a megaflood that ripped across the already scarred plateau. Evidence for this pulsing rhythm is written in layers. In some canyons, geologists find not one set of giant ripples, but multiple, stacked atop one another, separated by layers of fine silt. This tells a clear story. A flood of incredible power scours the channel and leaves its massive ripples, then the water subsides. For years or decades, quiet lakes form in the deep channels, allowing fine sediment to settle out like a gentle snowfall. Then the next flood arrives, roaring through, carving new ripples into that soft silt and the rock below before the cycle begins again. This was not a one-time rewriting of the landscape. It was a palimpsest, a manuscript scraped clean and written over, again and again, by a force of nature with a short, terrible memory. This realization transforms the Scablands from a monument to a single anomaly into a chronicle of a recurring planetary process. If it happened here, in the quiet of the Pacific Northwest, where else on Earth might this violent script have played out? The story of the Channeled Scablands is not a solitary tale, but a single chapter in a global epic. From the frozen steppes of Siberia to the chalk cliffs of Europe, the fingerprints of ancient megafloods are scattered across the planet, revealing a pattern as profound as it is violent. In the Altai mountains of southern Siberia, geologists find a hauntingly familiar scene: giant ripple marks 40 feet high and gravel bars the size of office buildings sprawled across high mountain valleys. Here, another ice-dammed lake, this one holding the waters of the Chuya and Katun rivers, burst its glacial bonds repeatedly. The floods that poured forth were so powerful they did not just scour the landscape, they reshaped the very courses of rivers and left behind deposits of rock and sediment so massive they are visible from space. This Siberian echo of the American floods proved that the process was not a local fluke, but a reproducible natural phenomenon, a recurring script written by ice and water on a continental stage. An even more dramatic rewrite of the map occurred at the edge of Europe. For most of human history, Britain was not an island. It was a peninsula connected to the continent by a wide, fertile plain now submerged beneath the English Channel. Near the end of the last ice age, a vast glacial lake pooled in what is now the southern North Sea, trapped against the retreating ice sheet to the north. When its natural dam finally gave way, the resulting spillover flood was a cataclysm of staggering proportions. A wall of water, combining with colossal meltwater flows from the Rhine and Thames rivers, ripped through the chalky bedrock connecting Dover to Calais. In perhaps just a matter of days, this single event carved the iconic White Cliffs and excavated the Channel Basin, permanently severing the land bridge and transforming the geography, ecology, and human history of an entire region. In a geological instant, a peninsula became an island, but the grandest actor in this global drama of flooding may have been a lake most people have never heard of. Glacial Lake Agassiz was a true inland sea, an ephemeral giant that once covered vast areas of central North America, from the Canadian prairies down into Minnesota and the Dakotas. At its maximum, it held more fresh water than all the lakes in the world today combined. as the ice sheets retreated, this colossal lake found new, catastrophic outlets to the sea. Its largest outburst, around 8,200 years ago, sent a volume of fresh water equivalent to 15 Lake Superiors roaring into the North Atlantic Ocean in less than a single year. The impact of this freshwater pulse was so immense it likely disrupted global ocean currents, including the crucial conveyor belt of the Gulf Stream, and may have triggered a centuries-long period of abrupt climate cooling known as the 8.2 kiloyear event. This was a megaflood whose consequences echoed far beyond its local landscape, rippling through the very climate system of the entire planet. These events, from Washington to Siberia, from the English Channel to the Canadian Shield, tell us something fundamental. Catastrophic megafloods are not geological curiosities. They are a key part of Earth's operating manual, especially during the volatile climatic swings of ice age cycles. They are the planet's pressure release valves, moments where pent-up energy from shifting ice and pooled water is discharged in a violent, landscape-altering rush. Recognizing this pattern forces us to see the familiar contours of our world in a new light, not as features carved with infinite patience, but as the dramatic aftermath of history's most powerful days. But how does a fluid we drink and swim in become a planetary scale chisel? The destructive power of a megaflood lies in a simple, terrifying equation. It is not just about water, but about water moving with impossible speed and unimaginable weight. Think of the difference between a garden hose and a fire hose. Both deliver water, but one has pressure and volume sufficient to knock a person off their feet. A megaflood is that fire hose scaled up to the size of a mountain range. The physics shift from gentle erosion to outright demolition. The first and most fundamental force is sheer velocity. When water moves fast enough, it stops flowing and starts plucking. In the Channeled Scablands, the bedrock is a dense volcanic basalt, a stone so hard it seems permanent. Yet the floodwaters, moving at estimated speeds of 50 to 60 miles per hour, did not slowly wear it down. They exploited natural fractures in the rock, and the pressure of hundreds of feet of raging water forced itself into every crack. This hydraulic pressure acted like a colossal crowbar, literally prying entire columns of basalt loose from the bedrock and sweeping them away. The landscape was not sanded down, it was dismantled piece by piece, with the flood treating solid stone like a loose tile floor. Then there is the phenomenon of cavitation. When water rockets over a rough surface at extreme speeds, tiny low-pressure bubbles form and then collapse with explosive force. In a normal river, this effect is negligible. In a megaflood, these microscopic implosions happen trillions of times per second against the bedrock, each one a tiny hammer blow. Over hours or days, this relentless percussion beats the rock into submission, scouring out deep, smooth-walled potholes. Some of these cavities in the Scablands are the size of swimming pools, drilled straight down into solid basalt by nothing but the focused fury of the water itself. But water alone is only part of the story. The true abrasive agent, the sandpaper of the apocalypse, was the sediment load. A megaflood is not clear water. It is a thick, roiling soup of mud, sand, gravel, and boulders. This transforms the fluid from a simple force into a grinding paste. The suspended sand and gravel act like countless cutting tools, sandblasting every surface the torrent touches. Larger rocks become battering rams, tumbling along the bottom with enough momentum to fracture and shatter anything in their path. This is how house-sized erratic boulders could travel hundreds of miles, not floating, but being dragged and bounced along in the bedload, their immense weight rendered irrelevant by the even more immense power of the flow around them. The process is a brutal synergy, the turbulent water plucking and weakening the rock, while the sediment within it grinds and polishes the scars smooth. It is a level of geological force we rarely witness, where the rules of ordinary rivers are suspended. and water becomes a tool for instantaneous, wholesale landscape surgery. The aftermath of such an event is a crime scene written across hundreds of miles, and the evidence is both monumental and strangely beautiful. To recognize a megaflood landscape, you must learn to read its unique fingerprints, a set of landforms so specific they could only be carved by a sudden, titanic rush of water. The first and most iconic clue is the giant current ripple. Forget the gentle undulations in a stream bed, these are geological waves. They stand up to 30 feet high with wavelengths, the distance from crest to crest stretching several hundred feet. They are made not of sand but of coarse gravel and cobbles. These ripples form only when water hundreds of feet deep moves at highway speeds across an open plain. The torrent sorts the rubble it carries, piling the heavier gravel into these immense, frozen waveforms. To stand beside one is to feel the scale of the current that built it, a force that treated truck-sized boulders as light sediment. Scattered across these scoured plains are what appear to be strange, teardrop-shaped islands, often with steep cliffs at their upstream end and long, tapered tails. These are streamlined islands, and they are the direct result of water obeying the same physics as air. Just as a fast-moving fluid flows smoothly around a wing or a racing car, the megaflood encountered large bedrock hills standing in its path. Instead of going over them, the incredible depth and speed of the flow went around, scouring the sides and the downstream flank with relentless efficiency. This sculpted the resistant rock into these aerodynamic forms, all pointing in the direction of the flood, like giant stone compasses forever indicating the path of the deluge. Perhaps the most dramatic signatures are the dry waterfalls. In places like Dry Falls in Washington, you can stand at the rim of a cliff over 3 miles wide and 400 feet high, staring into a vast, empty amphitheater. But there is no river at its base, only a silent plunge pool. This is the ghost of the largest waterfall that ever existed, dwarfing Niagara many times over. It formed when the flood encountered a sudden drop in the underlying basalt layers. The water didn't cascade, it collapsed as a single, thundering sheet, hammering into the bedrock below with such force it excavated a colossal basin. When the floodwaters drained away, they left behind this stark, empty stage, a monument to a performance that lasted only days. Along the margins of the main flood channels, you find immense, barren ridges of gravel and boulder, sometimes over 100 feet high. These are the catastrophic equivalent of river sandbars, but built to an absurd scale. These massive gravel bars formed where the flood's velocity suddenly dropped, often where the channel widened or turned. Just as a fast-moving river drops its sand load when it slows, the megaflood, choked with debris, dumped its immense cargo of rock in these towering piles. They are not gentle slopes but steep, chaotic berms of unsorted stone, a literal traffic jam of rubble left behind when the current could no longer carry it. All of these features combine to create the defining texture of the landscape, the scablands themselves. It is a torn, stripped, and chaotic terrain. The flood did not carve neat valleys, it ripped the earth apart, leaving behind a network of interwoven channels, buttes, and rocky basins. The topsoil and everything soft was utterly removed, leaving the raw, bruised bedrock exposed to the sky. This is not a landscape shaped by patient erosion. It is one that was violently disassembled. Each of these fingerprints, the giant ripples, the streamlined islands, the dry falls, and the colossal gravel bars, tells the same story on a different scale. Together, they form an undeniable narrative, a geological affidavit signed by water, rock, and unimaginable force. Far to the south of the glacial ice, another inland sea was forming under a desert sky. While Lake Missoula pooled against ice, a different kind of giant grew in the Great Basin of what is now Utah. This was Lake Bonneville, the ancient ancestor of today's Great Salt Lake, but on a scale that defies belief. At its peak, it was a true freshwater ocean, covering nearly 20,000 square miles and reaching depths of over 1,000 feet. Imagine a body of water so vast it submerged the modern cities of Salt Lake City and Provo under hundreds of feet of water, its shores lapping against mountain ranges we now see as dry islands in a desert. For thousands of years, it existed in a delicate balance, fed by mountain streams and melting glaciers, its evaporation rate matched by its inflow. But that balance was a temporary peace, and the landscape held a single, fragile point of failure. The lake's natural outlet was a low pass in the mountains near present-day Preston, Idaho, a place we now call Red Rock Pass. For centuries, water spilled gently over this sill, a manageable river flowing north into the Snake River system. Then, around 17,000 years ago, that gentle spill became a catastrophe. The prevailing theory suggests that the soft sediments at Red Rock Pass began to erode, perhaps triggered by a seismic shift or simply the relentless pressure of that immense volume of water. The outlet began to cut down, lowering the lake's spill point. This created a vicious, self-accelerating cycle. As the sill eroded, more water rushed out, which caused faster erosion, which released even more water. In a geological instant, the entire dam-like structure failed. The peaceful overflow transformed into a catastrophic breach, and the entire northern basin of Lake Bonneville began to empty itself in a roaring, unstoppable torrent. The quiet desert witnessed an event of almost incomprehensible violence. The volume of water that exploded through Red Rock Pass is staggering to contemplate. Estimates suggest the peak discharge reached nearly 35 million cubic feet of water every second. To put that in human terms, that is roughly 100 times the average flow of the Amazon River, the largest river on Earth today, concentrated through a single, collapsing gap in the mountains. This wall of water did not just flow, it rampaged. It tore across the Snake River plain of southern Idaho with the force of a planetary fire hose. The flood scoured the basalt bedrock clean, carving immense channels and leaving behind deposits of gravel and boulder that still form visible ridges and bars across the plain. These are the flood's calling cards, piles of debris so large they can be seen from the highway, silent testimonials to the day the desert drowned. The water did not just reshape the land it touched directly, it permanently altered the geography of an entire region. As the floodwaters charged into the Snake River Canyon near present-day Twin Falls, they encountered a plateau of solid rock. The river at that time was a modest stream flowing through a modest gorge. The Bonneville flood changed everything. The colossal influx of water and sediment overwhelmed the existing canyon, massively enlarging it. The floodwaters, armed with abrasive sediment and unimaginable hydraulic power, excavated the rock with brutal efficiency. In the process, they undercut the canyon walls, creating the breathtaking spectacle we see today, the majestic Snake River Canyon and its crown jewel, Shoshone Falls. Often called the Niagara of the West, Shoshone Falls is a direct legacy of that ancient flood. The waterfall exists because the Bonneville flood scoured out a deeper plunge pool and widened the canyon, creating the dramatic drop that persists even when the modern Snake River runs low. The entire canyon's grandeur, its sheer vertical walls and dramatic scale, was essentially rough cut in a matter of weeks by that single outburst. Lake Bonneville itself did not vanish, but it was forever diminished. The flood lowered the lake's surface by over 300 feet, stranding its former shorelines as crisp, parallel lines on the mountainsides around Salt Lake City, bathtub rings for a titan. It receded to become the smaller, saltier body we know today. This desert megaflood teaches a crucial lesson. These catastrophic rewrites are not exclusive to icy, glacial frontiers. They can happen anywhere a large enough body of water finds itself perched above a fragile outlet, whether that dam is made of ice, sediment, or bedrock. The story of our planet's surface is not just one of slow uplift and patient erosion. but also one of sudden, spectacular release, where landscapes we consider permanent are, in truth, just the calm aftermath of a forgotten cataclysm. The ghost of that desert flood finds its echo on the other side of the world, in the remote and rugged Altai mountains of southern Siberia. Here, far from the well-trodden paths of American geology, lies another testament to water's catastrophic power, written on a scale that rivals and may even surpass the great floods of North America. The Chuja and Katun river valleys wind through this stark landscape, but they are not ordinary mountain gorges. They are immense U-shaped troughs, their walls scoured smooth and their floors littered with chaotic deposits of rock. These valleys feel empty, too large for the modest rivers that now flow through them, like a giant's coat worn by a child. The most telling evidence, however, lies in what fills these oversized channels. Scattered across the valley floors are colossal gravel bars, some stretching for miles and rising hundreds of feet high. These are not gentle slopes of pebbles, but mountainous ridges of unsorted boulder and rubble, chaotic piles that speak of a current with no time to sort or settle its load. They are traffic jams of stone left behind when a force of unimaginable magnitude simply stopped. For decades, this bizarre terrain was a local curiosity, a dramatic but unexplained feature of a remote region. Then, in the late 20th century, geologists armed with the lessons from the Channeled Scablands arrived and recognized a familiar, terrifying signature. The Altai Mountains, they realized, had been the stage for a megaflood of staggering proportions. The script was the same, only the actors were different. During the last ice age, a glacier had advanced across the Chuja River Valley, acting as a perfect natural dam. Behind this wall of ice, water from the melting glaciers pooled to form a vast, deep lake. When the dam finally failed, the entire contents of this alpine reservoir were released in a catastrophic torrent that roared down the Chuja Valley and into the adjacent Katun Valley. The energy was so concentrated, the flow so deep and fast, that it did not merely flood the existing river channels, it completely overwhelmed and remodeled them. The flood scoured the valley walls, plucking massive blocks of rock and grinding the bedrock smooth, widening and deepening the gorges into the colossal spillways we see today. As the torrent slowed and spread out, it dumped its immense cargo of sediment, building those gigantic gravel bars in a single, violent depositional event. What makes the Altai flood particularly compelling is its potential scale. Some estimates, based on the size of the eroded channels and the volume of the deposits, suggest the peak discharge may have reached up to 10 million cubic meters of water per second. If accurate, this single event may have momentarily rivaled the combined flow of every river on Earth. The discovery was a profound validation of a global principle. Here, in a remote corner of Asia, geologists found the same suite of landforms, the giant bars, the scoured channels, the streamlined hills that Harlen Bretz had documented in Washington. It proved that the megaflood was not a unique American anomaly, but a reproducible planetary process. Wherever the right conditions existed, a high lake held by a fragile dam, the same catastrophic rewrite could occur, leaving behind an identical calling card written in gravel and stone. This Siberian echo tells us that our planet's most dramatic edits are written in a universal language. Yet even the immense power of Ice Age floods pales before a planetary-scale event that rewrote an entire ocean basin. This is the story of the Zanclean flood, a cataclysm that didn't just carve a canyon but resurrected a sea. For nearly 600,000 years, the Mediterranean Sea was not a sea at all. It was a vast, empty desert, one of the most dramatic transformations in Earth's recent history. A combination of tectonic shifts and falling global sea levels during the late Miocene epoch gradually pinched off the Mediterranean's connection to the Atlantic Ocean at the Strait of Gibraltar. With its main water source severed, the inland sea began to evaporate under the relentless sun. It shrank and kept shrinking. The rivers of Europe and Africa, like the Rhone and the Nile, carved canyons thousands of feet deep as they chased the plummeting water level down to a briny, hyper-salty remnant. Eventually, the basin dried down to a series of scattered, toxic lakes, their beds crystallizing into layers of salt and gypsum miles thick. This period is known as the Messinian salinity crisis, a time when the map of the world looked utterly alien, with a colossal, sun-scorched depression sitting where one of the planet's great oceans should be. The evidence for this is locked in the geology. Today, ships with special equipment can take core samples from the Mediterranean seafloor. What they pull up is a startling record, a layer cake of history. Beneath the normal marine mud, they find immense, hardened deposits of salt, a mineral that only forms when a body of water evaporates completely. These salt layers are up to 2 miles thick in some places, a testament to an ocean that simply vanished. Then abruptly, that salt layer ends and normal marine sediments return. The line between them is not gradual, it is a sharp, violent boundary. Something happened to stop the drying, something sudden and overwhelming. That something was the Atlantic Ocean, patiently waiting on the other side of a crumbling dam. The refilling was not a gentle trickle. It was a catastrophic deluge that makes all other floods seem like ripples in a pond. For centuries, the Atlantic surface sat over 1,000 feet higher than the dry Mediterranean basin, held back only by a fragile natural sill of rock at Gibraltar. Erosion from Atlantic currents, perhaps combined with tectonic movement, finally wore that final barrier down. When it failed, it did so completely. The Atlantic Ocean began to pour into the continental scale hole. The physics are almost unimaginable. Water rushed through the newly opened gap with such force that it quickly eroded the channel wider and deeper, creating a positive feedback loop of even greater flow. Estimates suggest that at its peak, the waterfall over the Gibraltar sill was over 2,500 feet high, more than 5 times the height of the modern Angel Falls. The roar would have been audible for hundreds of miles. The basin filled at a rate that defies belief. Research suggests the Mediterranean Sea, which holds about 1 million cubic miles of water, was refilled in a geological blink, possibly in less than 2 years. To visualize that, picture the entire basin filling at a rate of over 30 feet per day. Coastlines would have retreated by miles every single hour as the newborn sea raced inland, drowning the vast salt plains and deep river canyons in a relentless, unstoppable advance. The energy released by this single event was on the order of thousands of times the world's entire annual energy consumption today, a force capable of reshaping continents. The impact of this planetary reset echoed far beyond the basin's rim. The sudden introduction of a vast, warm body of water where there had been only desert would have dramatically altered regional weather patterns, likely triggering intense storms and shifting rainfall across southern Europe and North Africa. But the effects may have been global. Pouring that much relatively fresh water from the Atlantic into the Mediterranean would have changed the salinity and density of the Atlantic itself, potentially disrupting ocean currents on a hemispheric scale. This could have triggered rapid climate shifts, cooling some regions and warming others, all within a humanly imperceptible span of years. For biology, the event was a mass extinction followed by an explosive recolonization. The unique, hyper-saline ecosystems of the Messinian lakes were obliterated in an instant, drowned by the invading Atlantic waters. But as the new sea stabilized, Atlantic marine life rushed in through the open strait, seeding the Mediterranean with the ancestors of the species we see there today. The deep, dry canyons carved by the Nile and Rhone became submerged estuaries, creating entirely new habitats in a flash. The Zanclean flood stands as the ultimate testament to catastrophe as a creative force. It reminds us that the familiar contours of our world, the very seas that define continents, are not permanent. They are the aftermath of a single, terrible, and breathtaking day in the life of our planet. The story of Earth's great floods does not end at our own shorelines. It extends into the cosmos, rewriting our understanding of a neighboring world. For decades, planetary scientists staring at images from Mars saw something hauntingly familiar. Across the red, dusty plains, they observed vast, dry channels, some dwarfing the largest river systems on Earth. The most famous of these, Kasei Valles, is a colossal scar stretching nearly 2,000 miles long and, in places, over 200 miles wide. Its features were bizarre, yet they echoed a pattern first decoded in the deserts of Washington and Siberia. The channel floors were scoured clean, littered with teardrop-shaped islands and what appeared to be immense, washed-out basins. These were not the gentle, meandering valleys carved by a persistent river over eons. They were the unmistakable fingerprints of a catastrophic outburst, a landscape torn apart in a sudden, violent release. The discovery was a revelation. The same toolkit geologists used to read the Channeled Scablands, the understanding of streamlined islands, chaotic terrain, and dry cataracts, became the key to translating the ancient history of Mars. Here was evidence written across an entire hemisphere that water had not just trickled on Mars, but had exploded across its surface with a fury that makes our own megafloods look like garden spills. The scale is almost incomprehensible. The channels on Mars suggest discharges of water that could have been 100 to 1,000 times greater than the largest floods known on Earth. To carve such features, the water would have needed to be not just fast, but deep, perhaps forming torrents hundreds of feet high, thundering across the landscape for weeks or months. This pointed to a source of water equally colossal. Scientists theorize that these Martian outflow channels were likely born from the catastrophic failure of immense underground reservoirs. Imagine vast aquifers of liquid water, or perhaps pressurized mixtures of water and mud, trapped beneath a frozen surface and sealed by a layer of permafrost. A massive impact from an asteroid or the heat from volcanic activity could have suddenly melted that seal. The result would be a titanic, pressurized geyser erupting from the ground, not of lava, but of liquid water and debris, flooding out across the plains with unstoppable force. This interpretation forces a dramatic rethink of ancient Martian climate. A planet capable of generating such floods could not have always been the cold, bone-dry desert we see today. It suggests a past where Mars was warmer, or at least periodically unstable, with vast stores of liquid water lurking beneath its surface, waiting for a geological trigger to set them free. The story of Earth's megafloods, once a heretical idea, thus became a universal decoder ring. It taught us to recognize the signature of catastrophe not just on our world, but on any world where rock and water have met. The ghosts of those Martian deluges now stand as silent testimony to a time when the red planet was a place of sudden, terrifying change. Its history written in channels that whisper of a lost and very wet chapter in the life of the solar system. The script for these cataclysms always begins with a dam, not one of concrete and steel, but a natural barrier holding back an impossible weight of water. While the specific stories vary from continent to continent, the underlying trigger follows a chillingly simple pattern. A vast volume of water becomes trapped, its energy potential building for centuries. Then the dam fails, and that pent-up energy is unleashed in a single, furious instant. The most common actor in this drama, the one responsible for the floods of Washington and Siberia, is the glacial ice dam. Picture a slow-moving river of ice, an advancing lobe of a continental ice sheet. It grinds its way into a mountain valley, completely blocking a major river system. The water flowing into that valley has nowhere to go, so it begins to pool. For hundreds of years, it rises, creating a deep, cold lake held in place solely by a wall of ice. This dam is not static. It is under constant, immense pressure from the water behind it. The lake seeks any weakness, seeping into cracks in the ice, warming it from within. Eventually, the dam reaches a tipping point. Perhaps a slight climatic warming softens the ice, or the sheer hydraulic pressure causes a section to buoy upward. The failure is catastrophic and rapid. The ice doesn't just crack, it disintegrates, unleashing the entire lake in a roaring, unstoppable outburst. This process can repeat like a geological heartbeat as the ice sheet advances to dam the valley once more, setting the stage for the next flood. But ice is not the only material nature uses to build these temporary, deadly reservoirs. In the volcanic landscapes of New Zealand, a different kind of dam once held back a lake of tremendous scale. Around 26,000 years ago, the colossal Oruanui eruption at what is now Lake Taupo spewed out so much material that it formed a natural dam of volcanic rock and ash across the nearby Waikato River. Behind this barrier of cooled lava and compacted debris, a huge lake formed. When this volcanic dam eventually succumbed to erosion or a secondary collapse, it released a megaflood that scoured the river valley for over 100 miles downstream, leaving behind deposits of pumice and distinctive sediments that geologists can still trace today. This event reminds us that the planet's fiery interior can also set the stage for its most devastating floods. Perhaps the most precarious dams of all, however, are those built by the land itself. Across the globe, earthquake-triggered landslides have often tumbled into river valleys, creating immense, unstable piles of rock and soil that block the flow. One of the most studied examples of this occurred in North America near the end of the last ice age. A catastrophic rockslide, likely caused by the destabilization of slopes as glacial ice retreated, sent an avalanche of debris crashing into the ancient Wisconsin River. This formed a massive landslide dam behind which a substantial lake pooled. When this earthen dam, saturated with water and lacking any internal structure, finally breached, it released a powerful flood that carved through the landscape of what is now the dells of the Wisconsin River, creating its famous narrow gorges and striking rock formations in a geological flash. Whether the dam is made of ice, fire, or fallen rock, the narrative arc remains the same. A colossal volume of water is impounded, its escape route blocked by a temporary, fragile plug. The pressure builds until the plug gives way, rewriting the downstream landscape in a matter of days. This recurring plot reveals a fundamental truth about our planet, that its most stable-looking features often hide a history of sudden, spectacular release. This recurring cycle of damming and destruction was not a random act of chaos, but a direct product of the planet's shifting climate. The Great Ice Ages, particularly the Pleistocene epoch that ended just 12,000 years ago, were not merely periods of cold, they were megaflood factories. The relentless advance and retreat of continental ice sheets across North America and Eurasia created the perfect, repetitive conditions for these catastrophic releases. An ice sheet is more than a static blanket of snow, it is a dynamic, continent-scale sculptor. As it grows, its immense weight grinds over the land, bulldozing soil and rock, and fundamentally altering drainage patterns. But its most crucial role in this story is that of a dam builder. Imagine the edge of the ice, a towering, dirty cliff of ice hundreds of feet high, slowly oozing forward into a major river valley. It acts as a perfect plug, blocking the river's path to the sea. With its escape route sealed, the meltwater from the ice sheet's own surface, combined with water from rivers trapped behind it, has nowhere to go but up. This is how the vast proglacial lakes like Missoula and Agassiz were born, pooling in the depressed landscapes just south of the ice margin. These lakes were not permanent features, they were transient giants, their lifespans dictated entirely by the behavior of the ice dam that created them. And that behavior was intimately tied to the climate's delicate dance. The ice ages were not a steady, unbroken freeze. They were a series of dramatic oscillations, periods of intense cold called glacials, interrupted by shorter, warmer intervals known as interglacials. Within these broad swings were even more rapid pulses, centuries-long warm snaps and cold reversals. Each warming pulse, however slight, sent a signal through the entire system. The edge of the ice sheet would begin to melt and thin. The lake behind it, sensing this weakness, would press harder, its waters potentially seeping underneath the ice or lifting it flotationally. The dam, now compromised, would eventually reach a breaking point. The result was a catastrophic outburst flood, a sudden, violent release of pent-up water that had been accumulating for centuries. Then, as the climate cooled again, the ice margin might re-advance, once again blocking the river valley, and the slow, patient process of refilling the lake basin would begin anew. This made megafloods a predictable, if terrifying, part of the glacial cycle. They were the pressure valves of the Ice Age world, inevitable releases of energy that occurred whenever the system became too unbalanced. The timing of these floods was not random. It was locked in rhythm with the planet's climatic heartbeat. Sediment cores from the North Atlantic, for instance, show layers of distinctive gravel and rock that were carried far out to sea by the immense freshwater pulses from Lake Agassiz. These layers correspond neatly with known periods of abrupt climate cooling, suggesting that the floods themselves could deliver such a shock of fresh water to the ocean that they disrupted global current systems and tipped the climate into a new state. So these events were not just consequences of climate change. They were powerful agents of it, capable of feeding back into the system and altering the course of global weather patterns for centuries. The Ice Age landscape was therefore in a constant state of tension, a slow-motion battle between the accumulating power of impounded water and the fragile integrity of its icy walls, a battle that was decided again and again in a geological instant. The evidence scattered across continents is undeniable, but the sheer physics of these events once seemed beyond calculation. How do you measure a catastrophe that vanished millennia ago? Today, we don't just read the geological crime scene, we reconstruct the crime itself using a powerful digital tool, the hydraulic model. Scientists now feed the ancient landscape, in all its scarred detail, into sophisticated computer simulations. They begin with the modern terrain, a digital map of the Channeled Scablands or the Altai mountains, and then use geological clues to digitally restore the pre-flood topography. Next comes the crucial variable, the water. Researchers estimate the volume of the vanished lake, whether it's Glacial Lake Missoula or its Siberian counterpart, and program that colossal mass into the model. Then, with a digital representation of the broken ice dam, they release the flood. What unfolds on screen is not an animation for spectacle, but a rigorous physics experiment. The software calculates the behavior of that water as it obeys the unbreakable laws of fluid dynamics. It shows where the torrent would accelerate as it funneled into narrow canyons, predicting flow speeds that match the evidence of plucked bedrock and transported boulders. It visualizes where the water would slow and dump its immense sediment load, forming the precise locations of those gigantic gravel bars we find in the field. The models reveal the flood's depth, painting a picture of water hundreds of feet deep drowning entire mountain ranges, and its erosive power, highlighting which rock layers would be stripped away and which would be left as solitary islands. This digital reenactment does more than just create a compelling visualization. It validates the field geologists' observations in a powerful way. When the model's predicted path of maximum destruction aligns perfectly with the most severely scoured channels on the map, it's a profound confirmation. When the simulated water depths required to form the giant current ripples match the depths indicated by the high water marks on canyon walls, the hypothesis moves from likely to virtually certain. These models allow us to quantify the unthinkable, to attach numbers to the raw. We can now say with confidence that the peak discharge of the Missoula floods reached 10 cubic miles of water per hour, or that the water raced across the plains at highway speeds. They transform the floods from a terrifying abstraction into a quantifiable, understandable, though no less awe-inspiring force of nature. By running these simulations, we are not just watching the past, we are testing our understanding of it, proving that the language of water and stone, when decoded by modern science, tells a consistent and spectacular story. These digital deluges lead us to a profound and deeply human question. If the last of these great floods occurred as recently as 8,000 years ago, is it possible that our own ancestors stood on high ground and watched the world change? This idea sits at a controversial crossroads, where hard geological evidence meets the fragile threads of human memory. We know with certainty that people were present across the landscapes reshaped by these events. In North America, the final, colossal outburst from Lake Agassiz swept across the continent just as the first human communities were establishing themselves in the wake of the retreating ice. These were not empty lands awaiting a flood, they were becoming home. The timing is so close it feels like more than coincidence, it feels like a shared chapter. Could the thunder of a collapsing ice dam, the sight of a horizon replaced by a moving wall of water, have been a real, lived experience for early generations? The geological record gives us the fact of the flood, but it cannot tell us if there were eyes to see it. This is where the conversation turns from stones to stories. Around the world, across cultures with no possible historic contact, there exists a strikingly common narrative, the story of a great flood. From the Mesopotamian epic of Gilgamesh to the biblical account of Noah, from flood myths in the Americas to legends in ancient China and Australia, the motif of a cataclysmic deluge sent to reshape humanity is a near-universal theme. For a long time, scholars viewed these as purely symbolic tales, metaphors for chaos and rebirth. But the discovery of real, planet-altering megafloods in our recent geological past invites a tantalizing reinterpretation. Could these myths be distant, distorted echoes of actual events? The theory suggests that a traumatic, landscape-altering event like the rapid filling of the Mediterranean or the repetitive flooding of continental river systems could have been so catastrophic that it became embedded in the foundational stories of surviving populations. The memory, passed down over hundreds of generations, would inevitably transform, blending real details like rising waters and a desperate search for high ground with cultural symbols, moral lessons, and deities. It is crucial to draw a clear line here, one that separates scientific inquiry from speculation. Geology provides the evidence for the floods. Archaeology places humans in the right place at the right time. But the link to specific myths remains in the realm of compelling possibility, not proven fact. We cannot dig up a story, we can only notice the resonance. This distinction is important because it keeps the science rigorous while still honoring the profound human impulse to make sense of catastrophe. Whether these global stories are direct memories or simply a shared human response to the power of water, they highlight something fundamental. Our species has always lived on a planet capable of sudden, breathtaking violence. The floods that rewrote the land may have also written themselves into our oldest narratives, a reminder that the ground beneath our feet and the stories we tell about it are both deeper than they seem. The aftermath of such a deluge is not just geological, it is profoundly biological. When the last of the floodwaters drain away, they leave behind a world stripped to its skeleton, a landscape of raw, scoured bedrock and fresh, barren sediments. It is a blank slate of almost total destruction, an ecological ground zero. For the plants and animals that once lived there, the event is an absolute end. But for life as a force, it is also a dramatic new beginning, the opening scene of a story called primary succession. This is the process by which life painstakingly recolonizes a place where no soil, and often no trace of previous life, remains. It starts with the pioneers, the first hardy colonists capable of surviving in a mineral desert. On the freshly laid gravel bars and damp scoured rock of a post-flood landscape, the first signs are often lichens and mosses. These are not plants in the traditional sense, but symbiotic partnerships between fungi and algae. They need no soil, they can cling to bare stone, and through their slow, patient chemistry, they begin the monumental task of building it. Over decades, they secrete acids that subtly break down the rock, and when they die, their tiny bodies add the first whispers of organic matter. This creates a thin, crude precursor to soil, just enough for the next wave, perhaps some tough grasses or hardy herbs with shallow roots. Their life cycles add more organic material. Their roots help to stabilize the loose sediments, and slowly, year by year, century by century, the sterile gravel transforms into a thin, living soil. Shrubs and then trees follow, each generation altering the environment just enough to make it hospitable for the next, in a slow, beautiful march from devastation to forest. This process can take centuries or even millennia, a quiet, persistent counterpoint to the violent instant that created the opportunity. But the floods did more than just destroy and reset. They engineered entirely new habitats. In the Channeled Scablands, the unique conditions carved by water created ecological islands. The deep, scoured basins, known as plunge pools, often filled with water to become permanent lakes or seasonal wetlands, isolated oases in the dry shrub steppe. The steep, north-facing canyon walls created cool, shaded microclimates, while the sun-baked south-facing slopes became arid deserts just feet away. This patchwork of extremes fostered a remarkable diversity of life. Unique plant communities evolved in these isolated pockets, species found nowhere else on Earth, endemic survivors that adapted to the strange, flood-sculpted world. The Scablands are now home to rare wildflowers, grasses, and insects that treat this scarred landscape not as a wound, but as their exclusive, irreplaceable home. The flood, in its terrible creativity, did not just carve rock, it carved the potential for new life, setting in motion an ecological story that is still being written, one quiet year at a time. The final, enduring testament to these floods is carved into the border between two states. The Columbia River Gorge, with its sheer cliffs and thundering waterfalls, is often celebrated as a monument to slow, persistent erosion. But its deepest cuts, its most dramatic scale, were the work of a furious, repeated assault. As the last of the glacial lakes emptied, the titanic floods from Lake Missoula were funneled into a single, narrow exit, the only path to the Pacific Ocean, the ancestral Columbia River channel. What happened there was less like a river carving a canyon and more like a fire hose blasting through soft clay. The normal Columbia was a powerful river, but the megafloods multiplied its force 1,000-fold. Each catastrophic pulse did not just flow through the gorge, it scoured and widened it with brutal efficiency. The floods exploited weaknesses in the bedrock, ripping away entire cliffsides and undercutting the walls. This amplified the gorge's depth and steepness dramatically, creating the iconic, towering basalt faces we see today. The water moved with such velocity and depth that it overtopped the southern wall of the gorge in several places, carving a series of spectacular waterfall alcoves in the process. Multnomah Falls, Bridal Veil Falls, and the others that grace the Oregon side are not just products of rainfall. They are the direct legacy of floodwaters that briefly took a shortcut, plunging over the rim and carving their amphitheaters into the cliff face before the main torrent receded back to the main channel. The floods left more than just scars on the landscape, they left their cargo. As the torrent finally slowed near the Pacific, its immense power waned, and it began to drop the heaviest stones it had carried for hundreds of miles. This is why today, on the far western end of the gorge and even out onto the plains near Portland, you can find enormous boulders of a distinct granite and metamorphic rock. These stones have a geological fingerprint that matches the mountains of Montana and Idaho, the very heart of the flood source. They are silent, stranded travelers, permanent monuments to a journey that began with the collapse of an ice dam and ended here, resting where the current finally released them. In this way, the Columbia River Gorge is a palimpsest, a story written over itself. The patient work of the river wrote the first draft over millions of years, but the furious, repeated edits of the Missoula floods penned the final, dramatic chapters that defined its grandeur. Even with overwhelming evidence, the story of these floods is far from a closed book. Science thrives not on final answers, but on the questions that keep us looking closer. Today, researchers are still debating the finer details of these cataclysms, and their discussions reveal just how complex reading the planet's past can be. Take the Missoula floods themselves. We know they happened repeatedly, but the exact number is a subject of active investigation. Was it 40 separate outbursts or 80 or somewhere in between? The answer lies in those layered sediments in the Scabland channels. Each flood deposit tells a story, but over thousands of years, some layers can be eroded away while others might blend together. It's like trying to count the pages of a book that has been left out in the rain. Some pages are fused and others are missing entirely. Geologists use sophisticated techniques, from analyzing the magnetic minerals in each layer to dating microscopic volcanic ash particles, to try and separate each individual pulse of water. This debate isn't just academic. It helps us understand the rhythm of the Ice Age climate, how often it reached a tipping point that sent a wall of water racing across the continent. Then there is the question of sheer power. Calculating the peak discharge of these floods, the maximum volume of water moving per second, is a monumental physics puzzle. Estimates for the largest Missoula floods range from about 10 million to over 20 million cubic meters of water every second. That range is enormous. It represents the difference between a catastrophic event and an almost inconceivable one. Refining these numbers involves ever more detailed computer models and a deeper understanding of how water behaves when it is hundreds of feet deep and moving at highway speeds. Did the water move as a single, coherent sheet, or did it surge in chaotic, turbulent waves that focused its energy in unpredictable ways? The quest to pin down these numbers is a quest to truly measure the scale of a force we can barely imagine. Beyond these established events, some proposed megafloods remain in the realm of compelling hypothesis, awaiting definitive proof. One of the most discussed is the idea of a catastrophic flood filling the Black Sea around 7,600 years ago. The theory suggests that as global sea levels rose at the end of the last ice age, Mediterranean waters eventually spilled over the Bosporus sill, transforming a freshwater lake into the saltwater sea we know today in a rapid, dramatic event. While some marine cores show evidence of a sudden shift, other studies suggest the change was more gradual. The debate is vigorous, with scientists meticulously examining sediment layers on the seafloor, looking for the telltale signs of catastrophic erosion or sudden changes in fossil types that would signal a deluge. This is science in action, a slow, careful process of gathering evidence, challenging interpretations, and refining the story. These controversies are not signs of weakness in the theory of megafloods. They are its greatest strength. They show a field that is alive, constantly testing its own conclusions against new data. Every debate, every unanswered question, is an invitation to look at the landscape with fresh eyes and to remember that the history of our planet is written in a language we are still learning to read with perfect clarity. The evidence is all around us, but seeing it requires a specific kind of vision. To piece together the story of a geological instant, scientists must become detectives, reading a crime scene that spans continents and millennia. Their toolkit is a blend of high-tech observation and old-fashioned fieldwork, each method revealing a different piece of the puzzle. It begins with a view from space. Satellite imagery and LiDAR, which uses laser pulses to map the ground surface in exquisite detail, allow researchers to see the large-scale patterns invisible from the ground. From this vantage point, the sprawling network of the Channeled Scablands or the immense gravel bars of the Altai Mountains snap into focus as coherent systems. These technologies strip away the forests and the soil, revealing the bare bones of the landscape, the giant ripple marks and dry waterfalls that tell of water moving on an impossible scale. This bird's eye view provides the map, but the clues themselves must be examined up close. That is where field geology comes in, the boots-on-the-ground work of walking the channels, measuring the height of a gravel bar, or tracing the path of an erratic boulder back to its source. By meticulously mapping these landforms, geologists can reconstruct the flow's direction, its speed, and its relative power, reading the story written in stone. Yet a landscape's shape only tells part of the tale. To understand the sequence of events, you must look at what lies beneath. Sediment core analysis is like taking a biopsy of the Earth's history. By extracting long cylinders of mud and sand from lake beds or floodplains downstream from a proposed flood source, scientists can find the direct fingerprints of the catastrophe. A normal, quiet lake deposits fine, layered silt, but within that orderly record, they might find a sudden, thick layer of coarse sand and pebbles, material that could only have been dumped by a violent, high-energy current. That distinct layer is a flood deposit, a time capsule of the event itself, sandwiched between centuries of calm. But perhaps the most elegant tool in the kit answers the most crucial question: when? For that, geologists turn to the sky not for imagery but for a constant rain of cosmic rays. This is cosmogenic nuclide dating. When a megaflood scours a landscape, it exposes fresh bedrock to the open air for the first time in millennia. From that moment, the newly exposed rock is bombarded by high-energy particles from space, which slowly create trace amounts of rare isotopes within the mineral crystals, like beryllium-10 or aluminum-26. By carefully sampling that scoured bedrock and measuring the precise buildup of these cosmic clocks, scientists can calculate exactly how long ago the flood stripped the land clean, exposing that surface to the sky. It is a way of dating the moment of the catastrophe itself. Together, these methods form a powerful synthesis. Satellites provide the grand pattern, field mapping deciphers the mechanics, sediment cores capture the deposits, and cosmic dating pins it all to the calendar. It is a forensic process that transforms a silent, scarred landscape into a vivid narrative, allowing us to witness, with scientific certainty, a day of unimaginable power that happened thousands of years before the first cities were built. The scars left by those ancient floods are not just barren rock, they are the very foundations of life in the modern Pacific Northwest. The same catastrophic waters that tore the Channeled Scablands bare also delivered a gift of immense fertility hundreds of miles to the west. As the Missoula floods roared toward the Pacific, they hit a natural bottleneck at the Columbia River Gorge. Here, the torrent slowed and spread out, dropping its immense suspended load of finely ground rock flour and rich minerals scoured from the volcanic plains of eastern Washington. This silt-laden water was then swept by normal river currents into the broad, calm basin south of Portland, the Willamette Valley. Over dozens of floods, this process deposited layer upon layer of incredible soil, creating a loamy, nutrient-dense bed sometimes over 100 feet deep. This is not ordinary dirt, it is the direct sediment of catastrophe, a geological inheritance that made the Willamette Valley one of the most agriculturally productive regions on Earth. The vineyards, orchards, and farms that define Oregon's economy today are rooted quite literally in the aftermath of those icy deluges. The floodwaters did not just deposit soil, they also carried travelers. Strewn across the valley floor from the outskirts of Eugene all the way to Portland sit massive boulders of foreign rock. These are the famous Willamette Valley erratics, including the monumental Willamette meteorite, which is actually a glacial erratic carried within the ice that dammed Lake Missoula. These solitary stones are permanent landmarks, resting where the flood's last whispers of current finally released them, marking the high water line of a force that reshaped an entire biome. Further east, the legacy of a different flood defines the drama of the Snake River Canyon. The Bonneville flood's catastrophic rush did more than just excavate a larger gorge. It created the stage for one of North America's most spectacular natural features. As the floodwaters charged across the plain of southern Idaho, they encountered the resistant basalt layers at Twin Falls. The unimaginable hydraulic force, armed with abrasive sediment, undercut the canyon rim at this precise point. This undercutting created the conditions for Shoshone Falls, a majestic curtain of water that plunges over a sheer cliff even when the river is low. The falls, and the sheer, towering walls of the canyon itself, are not the work of the modest Snake River alone, but of that single, violent pulse from Lake Bonneville that did the heavy sculpting in a geological instant. The canyon's tourism, its iconic beauty, even the hydroelectric potential harnessed along its length, are all downstream consequences of that desert sea's sudden release. On a broader scale, the very topography that dictates where cities were built and how people move across the Pacific Northwest is a flood-sculpted map. The deep, direct route of the Columbia River Gorge, a vital transportation corridor for trains and highways, was dramatically widened and deepened by the repetitive Missoula floods, making it a more effective passage through the Cascade Mountains. The network of dry coulees and channels east of the mountains created unique, defensible sites for human settlement and later, for the sprawling farms that rely on irrigation drawn from waters flowing through those ancient spillways. Even the challenging, scabbed terrain itself, once seen as useless, is now recognized as a unique ecosystem hosting rare plants and animals that adapted to its harsh, flood-created microclimates. So when you look at a map of this region, you are not just seeing rivers and mountains, you are reading the aftermath of a series of planetary events. The fertile valley that feeds millions, the breathtaking canyon that draws visitors, the very paths our roads follow, all were set in motion by a force that lasted only weeks, a reminder that our modern world is often built upon the quieted footprints of ancient cataclysms. The power to rewrite a continent is not held by water alone. While the clearest signatures are carved by raging floods, Earth's history holds records of other catastrophic flows, events where the very ground itself became a fluid and raced across the landscape. To fully understand geological instantaneity, we must broaden our view beyond clear water to include the terrifying phenomena of Mega-Tsunamis and colossal debris flows. These are related chapters in the same violent story, where unimaginable volumes of mud, rock, and even ocean water move with enough speed and mass to redraw coastlines and bury mountainsides in a single day. Consider the Storegga Slide. Off the coast of Norway, beneath the North Sea, lies evidence of one of the largest submarine landslides ever discovered. Around 8,200 years ago, a massive section of the continental shelf, an area larger than Scotland, suddenly gave way. This was not a slow creep of sediment, but a catastrophic collapse that sent over 800 cubic miles of material sliding down the continental slope. The movement was so vast and rapid that it displaced an enormous volume of seawater, triggering a mega-tsunami that radiated across the North Atlantic. Waves estimated to be over 60 feet high would have smashed into the coastlines of Scotland, Norway, and Iceland, scouring shorelines and flooding low-lying areas that were just being settled by early human communities. The geological record here shows a sudden layer of marine sand and shells dumped far inland, a clear high watermark of a wave born from the collapse of the seafloor itself. This event shares the core DNA of a megaflood, a sudden release of stored potential energy that reshapes the world downstream. But here the fluid was a churning slurry of saturated sediment and the ocean it displaced. On land, similar processes occur as gigantic debris flows, often called lahars when they involve volcanic material. These are not rivers of water carrying rock. They are rivers of rock carrying just enough water to become a dense, concrete-like fluid. They can be triggered by volcanic eruptions melting glaciers, by intense rainfall on loose ash deposits, or by the catastrophic failure of a natural dam. Once in motion, a large debris flow is nearly unstoppable. It has immense mass, granting it terrifying momentum, and its dense consistency allows it to climb slopes and flow around obstacles that would halt a water flood. The Oso landslide in Washington state in 2014, though modern and small in scale compared to these prehistoric events, demonstrated the horrific power of such a flow, where a saturated hillside liquefied and traveled over a mile in minutes. Ancient examples are written into mountainsides around the world, in the form of vast, hummocky deposits of unsorted boulders and mud that blanket valleys far from their source. These flows are geological bulldozers capable of burying entire landscapes under hundreds of feet of rubble in a matter of hours. While distinct in their composition, what links a mega-tsunami, a submarine slide, and a massive debris flow to the story of the Channeled Scablands is the scale and speed of transformation. They are all expressions of a planet that occasionally and violently sheds its skin. They remind us that the solid ground we trust is part of a dynamic system where stability can be an illusion, and where change, when it comes, can arrive not just as a wall of water, but as a wave of earth or a mountain on the move. This realization reshapes our very sense of time and place. The story of our planet is not a slow, steady march, but a symphony of quiet patience punctuated by moments of breathtaking violence. For generations, geology was the study of the patient, the gradual drip of water that carved canyons over millions of years. The discovery of ancient megafloods was a revolution, a paradigm shift that forced us to accept a more complex and dramatic truth. It proved that the most profound chapters in Earth's history can be written in a geological instant, in a single season of unimaginable power. This new understanding gave us a master key. The suite of landforms first decoded in the Channeled Scablands, the giant ripples, streamlined islands, and dry waterfalls, became a universal translator. It allowed scientists to read similar stories in the mountains of Siberia, the deserts of Mars, and the floor of the Mediterranean Sea. We learned to recognize catastrophe not as a myth, but as a fundamental and recurring geological process, a pressure valve for a dynamic planet. This perspective changes our relationship with the ground beneath our feet. We walk on landscapes that are not permanent, but are the calm aftermath of forgotten storms. The fertile valleys, the dramatic canyons, the very paths of our rivers are often the legacy of a single, terrible day. It places humanity in a humbling context. Our entire recorded history is a thin sliver of time nestled in the quiet interval between these planetary pulses. We have built our civilizations on the still warm ashes of geological events we can scarcely comprehend. Yet this is not a cause for fear, but for awe and deeper curiosity. It invites us to look at the world with new eyes, to see the familiar contours of a hillside or the strange pattern in a desert not as static scenery, but as a page in an epic story. The call to action is simple: go and look for yourself. Visit these landscapes if you can. Stand at the rim of dry falls and feel the silence where a waterfall once thundered. Walk among the giant ripples of the Scablands and try to fathom the current that built them. Or simply look at a satellite map, trace the path of an ancient flood channel, and consider the force required to etch such a scar onto a continent. The evidence is all around us, written in stone and waiting to be read. By seeking out these stories, we do more than learn about the past. We begin to understand the profound and ever-changing nature of the world we call home.